Consider the general solution I'm going to bring into this problem, and you're going to see how it works. It's very simple. Okay, it's very, very simple. So let's start off with 23 and build into the rest of today. Right off the bat, I'm assuming that most of you guys can look at the problem and tell right away that you're going to add 2, divide by 4. We okay with that? So I'm going to say that sine squared is equal to 1/2. We okay with that? How do you undo square? Square root. So sine of x is going to equal plus or minus 1 over root 2. Whenever you take a square root over the equal sign, you got to put plus minus. Very easy to forget to do that. Now, when I'm trying to figure out my angles, is it easier for me to rationalize or not to rationalize? It's easier not to. And I'll show you why here. If you rationalize, not a big deal. You're going to get x is equal to the inverse sine of plus or minus 1 over root 2. The reason I'm not rationalizing is the following. What triangle am I working with the root 2s? Working with 45s. The sine of 45 is 1 over root 2. It's telling me that right off the bat without having to rationalize it. I don't have to do any extra work. All right? So I know that I'm working with a 45-degree angle. But I have to deal with radians. What's 45 radians? Pi over 4. Good. So I know that my value is going to be at pi over 4. This, again, is a skill that you guys are really good at from chapter 13, working with the reference angles. We know that pi over 4 is here. And I'm looking at plus minus. I'm dealing with sine. What other quadrant is sine positive in? Second quadrant. So the value in the second quadrant that has the reference angle of pi over 4 is what?
3 pi over 4.
Good. 3 pi over 4. So we have x is pi over 4, 3 pi over 4. Now I have to deal with the negative values. Sine is negative in the second and the fourth quadrant. What are my 2 angles there and there?
5 pi over 4.
Excellent. So we're at 5 pi over 4 and 7 pi over 4. Hopefully, when you did this problem, you got 4 answers. Now, here's what it means in terms of a general solution. What you guys did is you worked with your solution set, and you found it within 1 revolution of your circle. You found 4 happy spots. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. You found your 4 happy spots. Thank you. Your 4 happy spots were at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. What this is happening now is if I start at my first happy spot, how long does it take me to get to my next happy spot? Pi over 2. How long does it take me to get to my next happy spot? Pi over 2 and pi over 2. So in theory, the general solution here would have been pi over 4 plus pi over 2 n for however many times you're moving around the circle. The book writes it differently depending upon what your answers are. This fractional counter going around only the pi over 2 will work if you have plus minus at 45 degrees. It's the only time that'll work. Because if you look at your shape that's drawn here, this is a what? It's a square. So everything is congruent going all the way around. Therefore, you're moving the same amount each time. The moment I go up to pi over 3s and coming around like this, I'm working with rectangles, and it's not going to match up. So I can't do that shortcut of just adding on that small amount. I have to worry about adding pies, adding 2 pies, depending upon what I'm looking at. Okay. Freaky, man. Peace, dude. Whatever. All right. I'll stop. So, it's been a long day. I have to work a full week this week.
next week a full week?
No.
Half day Friday. What day do we get off?
We have half day Friday. So let's do this. Let's continue this work, and let's start with this one today. Let's build off of these 3 problems we did last night, and let's continue talking about general solution, and then I'm going to talk about what it means to be on an interval. We're going to do problems today that are still built into the circle, as well as what do you do when you can't find it on a circle? What do you do when you can't find it within our special right triangles? We have to remember how to press buttons on a calculator again. So we'll have a couple calculator problems today as well. Also, some factoring. Yep. Yep. So in this example here, does everybody agree to solve for this one out to get x by itself? The first thing I'm going to do, add 1, and then divide by the square root of 3. Is everybody okay with that? Do I have to rationalize that denominator?
No.
No. So I'm going to start this problem. Again, I'm looking at it. I know I have to divide, I have to add by 1 and divide by the square root of 3. I leave it like that because now I have to undo tangent. And how do you do that? Inverse. Very good. Which triangle am I working with 1s and root 3s? 30, 60. Very good. Which angle has the tangent of 1 over root 3? It's the 30. Excellent. 30 degrees in terms of radians then. Good. Like I said, you guys were really good at this. You guys were really good at solving the inverse stuff out given the triangle. That wasn't a difficult task for you. This tangent problem is positive. Do we agree? Tangent is positive within which 2 quadrants?
1, 3.
1 and 3. Good. So if this is pi over 6 for the reference angle in the first quadrant, what is the angle, therefore, in the third quadrant? Very good. What did you do to get to it? What did you do to get to here? You added pi. Does everybody see that? So to get to your happy spots, if I'm starting at a happy spot there at pi over 6, my other happy spot is at 7 pi over 6. What do I do to the pi over 6 to get here? What do I do to get back to it? What do I do to get to there?
Your happy spot's pi.
A happy spot is pi. Doesn't pi make everybody happy? So my general solution here, good luck, Morgan. My general solution then would be pi over 6 plus pi n for however many times you're moving around to get to a happy spot. All right. Have a good weekend. Okay? In this case, it works out that all I have to do is add pi to get to my happy spot, because it's just reflected over into that third quadrant. Sometimes it's not that clean. Okay? Not bad? Meh. Exactly. Is it chilly? Oops. Now let's make it weird. You know what? When you're doing these types of problems where solving the inverse stuff, I would write down my x, because that's my unknown, that's my variable, because I'm not simplifying anything here.
Yourself.
Right. So I have sine of x times tangent squared equals sine of x. What are you going to do first? Very good, very good. Divide both sides by the sine of x. What's sine of x divided by sine of x? 1. Now what do you do? Square root. Very good. What happens when you take the square root over an equal sign? Good. Now what? And inverse. What triangles can give you tangents of 1? It's the 45 scheme. Does everybody agree on that? Okay. So I know I'm going to get the 45 to get me the 1s. So when I draw it out, 45-degree angle is what in terms of radians? Very good. Pi over 4. Isn't this the next one? Isn't this the next one? Isn't this the next one? Yeah. Again, in this scenario, if I'm starting at pi over 4, if I add pi over 2 to that, I get 3 pi over 4, 5 pi over 4, 7 pi over 4. That's going to get me all of my possible solutions. So all I have to do is list out the first one, knowing that my happy place is going to go all the way around. Okay? It's one of those weird quirks that does happen from time to time, depending upon which angle you wind up at. Again, you guys were really good at working with reference angles and bouncing them off quadrants. That was never a problem for you guys. The only thing that's different that I'm changing up now is getting you to solve the equation to get to that point. Okay? Yes, sir.
A little bit off. What does 11 do?
This Social Security Administration is coming to help us out.
Cool.
It's awesome.
I don't know if I get that, but
That's okay.
alright.
So, what's different by putting this word on the interval mean, do you think?
On the
What's that? Yeah. Right. Nothing else changes, it's just between one revolution. So I don't have to worry about tacking on anything at the end of my answers. I'm looking for all possible solutions within one revolution. I don't have to write out plus pi n for anything. If it happened to be where it was tangent of plus minus 1, I would wind up writing pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and call it a day. I can't tack on anything else to it. I'm looking for all possible solutions within one revolution. So we have 4 times tangent squared x minus 1 is 0. If everybody's looking at that, does everybody agree you add 1, divide by 4? We okay with that?
Give me 1 over 2.
So I get tangent squared
1.
equals 1/4. How do I undo squaring? What's the square root of a 4? A 2.
A molar. That's funny.
That was funny. Plus or minus 1/2. Remember, it took a square root over the equal sign. Now, what do? Now, do we have a triangle that's going to give us a tangent of an angle that's a half? We don't, do we? Which means we have to use what?
Our calc.
We use our calculator. Okay? Now, the way that I've been explaining this throughout the day today is obviously, if I'm between 0 and 2 pi, what mode am I supposed to be in? I'm supposed to be in radians. But for the first time of explaining what is going on, I want you guys to be in degree mode. So I'm going to change this to degrees for a second. It's a little bit easier for students to see what's going on within the interval when you're dealing with the calculator if I show it to you in terms of degrees first, and then I'll re-explain it to you guys what it means in radians. Because after this one example in degrees, everything else will be radian, and it'll be pretty simple to work with. Okay? So we have inverse tangent of 1/2. If you type that in your calculator, as long as you're in degree mode, you should get 26.57. Did everybody get that?
I got 26.
26.57 for inverse tangent of a half?
Yep.
Okay. So my inverse tangent, I'm talking degrees, is 26.57 degrees. Now if I place that on a circle, that gives me the reference angle of 26.57 for it being positive. Do you agree? Okay. Where else is it positive?
Probably the
Third quadrant. All right, Caleb, how do I get from here to here? What do I have to add to this? Good. If I add 180 degrees to that, I get, okay. Now remember, this was a plus minus value, so I also had to worry about it being the negative quadrants. If 2657 is my reference angle, what would be the negative value for it in the second quadrant?
-153.
Careful. I'm going second quadrant.
153.4.
It's 180 minus it.
Oh,
Remember,
I did
it's
that
fine.
minus 180.
Yeah, when you come over to here, you take 180, subtract it to bounce it back up. Okay? So your second quadrant angle would be, what was it again?
153.43.
Okay. And then it would also be the same angle into the fourth quadrant. You can add pi to that if you'd like, or you could take and subtract out 360, you'll get the same value. Right? I mean add 180, I didn't even see. So you see radians. Does that make sense what you're looking at doing in terms of degrees? The only thing that's different than when you're working within radians on the calculator is that, remember, radians, when we're dealing with 30 degrees to radians, you'd multiply it by pi, divide it by 180, and you got this real nice, easy fraction to work with. Not anymore. If I'm starting with 26.57 times pi over 180, it's not going to give me a really nice, clean fraction. It's going to give me crappy fraction. And crappy fraction in your calculators look like crappy decimals. So switch your calculator back to radians real quick and retype in the inverse tangent of 0.5. Hit mode. You hit mode and just highlight where it says radian, make sure it's blocked out. Okay. And when you type in crummy fraction radian mode of that, you get crummy decimal of 0.46. Okay? Again, that just means it's some weird fraction that we don't know. But if you start to think about it, well, that's still got to be in the first quadrant because it's less than pi over 2. So if my 0.46 is my crummy radian, I'm up here. What do I add to it to get to that angle? In terms of radians? Pi. So my angles then would be 0.46, 0.46 plus pi,
Ah, sweet.
and I leave it like that. The crummy angle into the negative value, what do we subtract?
Pi minus.
Pi minus 0.46. And then to get it over here, what's the easiest way to get that?
2 pi minus.
Very good. Everybody here, see how that works? To bounce it down then, it would be 2 pi minus 0.46. So in this instance, since we're trying to find what angle has a tangent that's equal to plus or minus 1/2, that's just crummy decimals, crummy stuff. I have to use my calculator in order to do that. The calculator is not going to give me nice, clean values. I'm still using the same basic principles of bouncing my reference angles by adding pi, subtracting pi, or whatever. But do I need to press the buttons on my calculator to do that to get the decimal equivalent? Nope, just tack pi's in and you're going to be fine. Okay? Not so bad. You use your calculator if it does not fall into a nice triangle. That's the only time you have to worry about it. So that means if I have calculator, non-calculator part of the test, which I will, would this question be a non-calculator or a calculator? Calculator. You can't do it without. But the other ones you can do without a calculator, couldn't you? All right. Let's look at number 5. Again, on the interval, let me show you guys how to work with one that is an inverse. So if I start with this one, I'll let you guys write this down first. and I'll read. If I'm looking at the start of this problem, does everybody agree I would add 4, divide by 3? Yeah. Excuse me. Thank you.
Bless you.
Thank you. So I have secant squared of x equals 4 over 3. Everybody okay with that? Now there's one of two ways you can go about this.
Alright, I didn't put my name.
What would you do next? Square root it. If I take the square root of both sides, I get secant of x is plus or minus 2 over the square root of 3. Everybody okay with that? All right. Now, from there, what is secant? It's the opposite of cosine. So if I take the inverse on the left-hand side, the inverse of secant of x would be cosine of x. What would I have to do to the other side? Inverse it. What's the inverse of 2 over root 3? Excellent. Now what do you do? Now you move the cosine. What angle has a cosine of root 3 over 2 plus or minus? So first of all, which triangle are we going to get?
36.
Okay. Which one of those angles gives me the root 3 over 2 for cosine? The 30 degree. Everybody agree with that? So the 30 degree is going to give you the root 3 over 2. What is that in radians? Very good. So I have pi over 6. Now we have to worry about what angles are going to be pi over 6 to get this to work, plus and minus. Pi over 6 is here. Where else is cosine positive?
Fourth.
Fourth quadrant. So that would be at what angle?
7 pi.
11 pi over 6. So we have pi over 6. We have 11 pi over 6. That gave us both of our positive angles. Where is cosine then negative? Well, second and third. In the second quadrant, what is if the reference angle is pi over 6, what is your angle? 5 pi over 6, very good. And down here it is
7 pi over 6.
Now, this is the time where a lot of students try to go, oh, I just do pi over 6 plus 2 pi, or whatever, to get across everything. It's not the same interval each time because it forms a rectangle. It doesn't work. That only works at pi over 4s. So my other two answers then would be 5 pi over 6 and 7 pi over 6. I'm within one revolution. I don't have to worry about tacking on anything else, and I'm done. The trick here was solve everything like you would normally, flip that to the standard sine or cosine, whatever it might be, and it makes your life easier at that point. Could I have flipped it at secant squared and got cosine squared? Mm-hmm. You can do it at this point here, and then just get, cosine squared is 3 over 4, and then take your square roots. You're still going to get the same stuff after you flip them out and go from there. Okay? Now,
All we're doing, we don't have to do anything else with this problem?
no, you're done. You found all 4 answers.
Alright.
Okay. You found all 4 answers. What's going to happen, though, is that that's not the one you want to look at. what I'm gonna have you guys do, and I'm gonna give you the problems now, and I'm gonna give you this big giant hint for a couple of them. So on page 859, it's 25, 26, 27, 31, 4. There are 4 of them general solution, and there are 4 of them within one ringy-dingy, one revolution. Okay, so you don't have to worry about tacking anything on. But I do want to look at specifically.
Yeah, that's the direct shot that you would
I want you to look at 27. Can I put 27 up on the board? You guys all have these written down, okay? Thanks, Gabby. I'm going to show you guys a little trick here. This is a trick that you guys are going to get really familiar with when you get to pre-calc and then calculus. In order to start this problem, we would normally be setting the side equal to 0 because I've got a sine squared and a sine and a 1. So what I'm going to do is this. 2 sine squared x minus sine of x minus 1 is 0. I have sine squared, a sine, a constant. That's telling me I'm probably going to have to factor that as a trinomial. Now, there's a little trick in math called U substitution. What that means is that I'm going to let the letter U equal sine of x. By doing that, it cleans up the crappy looking trinomial to the following. 2u squared minus u minus 1 is 0. Now, it looks a little bit easier to factor. What's 2 times negative 1? So, what times what is negative 2, but if you add it together, you get negative 1.
Negative 2.
2 and 1. So I have 2u squared minus 2u plus 1u minus 1. And I can factor this by grouping, which is something we have done a long time ago. What's the GCF of 2u squared and a 2u? 2u too. What I've done here, by using that U substitution, I just made it a little bit cleaner to factor to make my life less complicated looking. So now when I rewrite this out, I have 2u plus 1, u minus 1, but since u equaled sine, 2 sine of x plus 1, sine of x minus 1 equals 0. How would you find zeros when you factored trinomials before? You'd set both terms equally 0, wouldn't you? What do you think's different here? Nothing. It's a little bit of a trick. It's called U substitution. You don't use it a ton in Algebra 2. You'll see it more and more in pre-calc, and then obviously they use this a ton in calc. Yes, sir?
So is it possible to get like 6 different answers?
Oh, yeah. Oh, yeah. Yeah, there's some examples in the book that use this U substitution that you wind up with if you have a 3rd degree polynomial, you could have 3 possible zeros. It's the same thing like we did with polynomial factoring before. Whatever the degree is, that's how many possible zeros you could get. Same present idea here, just for trade. Yes, sir?
Are there more homework problems that require that?
There's other homework problems that require factoring. I don't remember if there's one that uses the U substitution off the top of my head. Okay.
So how do you,
Set them both equal to 0 and solve for x.
so inverse sine?
The inverse sine of negative 1/2.
for that one.
Inverse sine of 1.